It's time to add a whole bunch of acronyms to your mind. HSRP, VRRP, and GLBP, which are all FHRPs. Did you get that? Say it 5 times fast. So I'm starting off by saying redundancy is good. Now the last time I said that was with Spanning Tree, because redundancy is good, but it could take down your whole network with Spanning Tree. This one not as devastating, but now we're moving up a layer. Spanning Tree is all about layer 2 switch infrastructure. FHRPs are all about layer 3. Now we're talking about IP redundancy. So redundancy is good, but it leaves us with a whole bunch of questions on how do we get there. We're going to start looking at all these different protocols, which all have the same goal, and find out what the differences are, and then we'll focus in specifically on HSRP and GLBP. Let's start off with that premise. Redundancy is good. Yes, it is. 2 is 1. 1 is none. That's always the mantra. If you have 2 servers, think of those as 1, because 1 could always go down. If you have 1 that goes down, you have essentially nothing left over. So when we're thinking about redundancy is good, we have to ask the follow-up question, well, what kind of redundancy? Well, all of those protocols, and I'll write them up right here, HSRP, VRRP, and GLBP are all focused around the same thing. Layer 3, or I guess more specifically, routing redundancy. What it allows us to do is create redundant routers. And we have to think of how things normally are. Let's say we want redundant connections to the internet, because most businesses nowadays, if the internet connection goes down, work is seriously prohibited. So we set up 2 routers. We maybe give this guy a .1 and this guy a .2 of the 10.1.1.0 network, right? And we say, okay, well, we're redundant. Well, yeah, but the problem is each client can only have 1 default gateway. So this guy is maybe hard-coded via DHCP or statically typed in to go to the .1 as his default gateway. What happens if that goes offline? You have the redundant router there, but now you either A, have to run around each client manually reconfiguring their default gateway, or B, reconfigure the DHCP scope and reboot all the devices so that they get the new default gateway. Either way, it's a lot of manual configuration. So all 3 of these protocols, their goal is to say, okay, well, that .1, instead of being assigned to that router and only that router, let's say we change that to a .3, it becomes a virtual IP address, .1, that both of these routers can respond to. Now, not at the same time, at least not for most of these protocols. We have to designate one of them as, we'll say, this is the active and this is the standby. So this guy is actively responding for .1, and if he ever goes down, like the purple X has shown, then the standby will take over and respond for the .1. So now this leads to a lot of questions. I just wrote some questions that I would have off the top of my head if I first saw this being presented. Well, how does a router know when to take over? Well, in all of the protocols you see right here, we have a new hello protocol that's introduced, a new type of hello protocol, where the standby is always checking in. He's saying hello, hello, hello. And you can configure that protocol for once every second, every 3 seconds, 10 seconds, every 100 milliseconds. I mean, you can go as low as you want to where he's going hello, always making sure that this active router is online. And if he stops hearing hellos back, the standby is like, okay, you're dead. I'm now taking over for the .1 IP address, and the traffic will start going over here. Now, how does the client switch? I mean, what needs to take place? Well, the good news is from the client's perspective, nothing has to happen. He's configured to go to the .1 IP address. The switch really happens on the gateway. So the clients are just going to the .1 like they always have. But now, for the deep thinkers, that brings up another issue. What about the ARP cache issues? ARP cache, well, what's that? Well, remember, every single time you go to an IP address, the computer has to send out an ARP message and find out what MAC address that thing has. So if he sends out an ARP for .1 and the active router says, oh yeah, my MAC address is 0010.1111.1111, and he dies and maybe his MAC address is 0010.2222.22, you get the idea, it's a different MAC address. Well, the problem is, yes, now he's got the right IP address, but the ARP cache lasts for 5 minutes. By default on most devices. So that's a 5-minute outage while we're waiting for this to time out and send another ARP message to get the new MAC address. Well, the designers of all these protocols thought of that and they said, okay, we're going to make not only the IP address a virtual IP address, we're going to make the MAC address a virtual MAC address as well. So from the beginning, this guy will never, let's say the active router here will never reply to an ARP message with his IP address. He'll always reply with this virtual MAC address. Did I say IP address? I meant MAC address. He'll never reply with his MAC address. He'll always reply with this virtual MAC address that the secondary router can take over if he goes offline. It's not actually his physical MAC address on his network card. Okay. So that's okay, we got that. We're feeling good. That pretty much makes sense how this guy can go. But wait a sec. If these guys are saying hello, 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 and maybe this active router doesn't go down. Maybe just the WAN link goes down to the ISP. Now the hello messages are still succeeding, right? So the secondary router still thinks he's online, but the internet link just went down. So is there a way of finding that, like tracking that interface? Absolutely. The way that we can do that is actually through something called interface tracking. Here's the way it works. Each one of these routers is given a priority. That's how they knew who became the active one to begin with. Let's just say this guy is given a 120 priority. This guy is given a, let's just say 100 priority. Higher priorities are better. The active router says, okay, I've become active because I've got 120, you've got 100, I win. So the standby is just watching, hello, hello, hello. We can configure interface tracking, and essentially what it says is, hey, you know what, if your, let's just say this is serial 0/0 link, ever goes down or becomes unreachable, or maybe you can even set up interface tracking where it pings an IP address out that interface every 5 seconds or 10 seconds or whatever interval you want to use. If pings ever stop out that interface, then I want you to subtract, well, whatever, as long as you drop it below 100, subtract 50, we'll say, from your priority. So if that interface goes down, he says, okay, I am decremented down to, what would that be, 70? 70. Now this next hello message comes over. He's like, you have now become lesser. The master has become the Padawan learner. And now the secondary is like, I will take over and I will preempt you. I will now become the active router because even though you're online, your priority just dropped below mine and now the computer goes out that way. So that's what they do. Now let's look at the 3 flavors of first hop redundancy protocols a little more in detail so we can tell what the differences are. I'm looking at those ice cream cones. I'm like, I just want to lick that strawberry one. Just looks delicious. So we'll call the strawberry one Hot Standby Routing Protocol. This was created by Cisco for Cisco in 1994. Isn't that amazing? 1994, a long time ago. This protocol is still one of the most popular ones still being used today. What its goal is, it's to create that virtual IP address between the two routers. So we've got the two routers, let's just say .1 IP address. Both of them are sending hello messages back and forth between, everything I just described. By default says hello once every 3 seconds. Hold down timer is 10 seconds. That means essentially we've got an active and a standby, and it's going to, if the standby doesn't hear a hello message from the active for 10 seconds, it's going to assume it's down and take over. Now in 1994, that was really fast. 1994, a 10-second outage did not bat an eye at any organization. But a little afterwards, about 5 years later, the rest of the industry caught up and they said, well, let's create the Virtual Router Redundancy Protocol, VRRP. What this is an industry standard flavor of HSRP that works on any vendor's router rather than just Cisco routers. So this one, when I say for Cisco by Cisco, that means it's proprietary protocol. VRRP is an industry standard, so you could mix a Cisco router and some heathen brand together in their own little redundancy cluster. Now, with that being said, I have never ever found somebody to do this. Initially you're like, oh, well, that's great, multi-vendor and all that. It's like, my goodness, why would you ever buy a Cisco? Well, first off, why would you ever buy anything but a Cisco router? But if you did, why would you ever mix vendors to where you've got this Cisco, whatever, 2900 series router or something that you're mixing with a Juniper? It's like, it doesn't make sense. You always buy these things in pairs for redundancy. They even have redundant packages sold cheaper. So the multi-vendor thing to me doesn't make much sense, but you can see right here, it was developed later. So we've got 1 second as the default hello timer and 3 seconds for the default hold timer or dead timer. So it's faster, but Now you might say, well, that's a clear advantage. Not really, because you could just go into HSRP and say, well, say hello once every second, or half second, or tenth of a second. You can adjust the hello timers to whatever you want for these protocols. So it isn't really an advantage, but I will say there is one distinct difference that I can say this might be an advantage to you. VRRP allows you to assign, let me draw up my little topology, to assign the virtual IP address as one of the IP addresses of the routers. So whatever we'll say your active router is, you can actually assign the virtual IP address as its IP address. And then we'll say the standby one is assigned .2, but it will take over for the .1 should that one go down. And the same, virtual MAC address, all that applies. The reason I say that might be an advantage is sometimes you've got situations like this. I shouldn't have made my ice cream cone so big. You've got two routers connected to, we'll say, the same ISP, to where, in actuality, they're kind of going into the same link together, and you have limited IP addresses right here on your WAN port. Sometimes this will save you an IP address. So you don't have to use a third. With HSRP, you cannot assign the virtual IP address as one. So maybe the active is .3, the standby is .2, and then you create this .1 virtual IP address sitting in the middle of them. It doesn't allow you to assign that as one. So that's I would say the only advantage of VRRP, which is an advantage if you have limited IP addresses. Now, GLBP. We're back to the created by Cisco for Cisco in 2005. Both of these guys, Check and Check, are literally identical except for the differences that I mentioned. They are meant to create an active standby relationship, whereas GLBP stands for the Gateway Load Balancing Protocol. It's the only one that allows for an active-active relationship. So that means that our computers can go through these routers on a load balancing basis. Maybe the first computer goes out the first router, second computer goes out the second router, third computer goes out the second router. You can kind of load balance between these two routers rather than just having one of them sitting there idle. Well, before we get into the configuration, let me get a little more technical behind the scenes and show the difference between HSRP and GLBP. VRRP we'll just kind of throw in the mix because it's identical to HSRP. So with HSRP, gateways are organized into what's called standby groups. Now, the reason they're called standby groups is that's the actual command you type in to configure them. You say standby and you give it a group number. So in order for these guys to join the same group, they need to be part of the same group number. So we'll just say these guys are part of standby group number 1. From there, we will set one of the gateways to be the active. The way we do that is based on the priority. So we'll say maybe this guy is priority 110, this guy is priority 100. So he becomes the active, he becomes the standby router. From there, we'll type in what we want the phantom or virtual router IP and MAC. You might say, where's this phantom coming from? That actually used to be what they called in the old documentation for HSRP. They always used to call it a phantom IP address instead of a virtual one, which I thought was so much cooler. And then, probably about 5 years ago, they started calling everything virtual, which I'm like, how many things use the word virtual? Not every day you get to say phantom IP address. So I'm going to go with it. I'm going to say we go in there and configure the phantom IP address between these two routers, and HSRP automatically generates a phantom MAC address. So we don't have to set that up. It just does it behind the scenes. And now the active router will respond to this IP address and hand out that phantom MAC address based on when an ARP request comes in. Now, from there, moving forward, by default, we can tweak this, but hello messages are sent once every 3 seconds. We're dead after 10 seconds. So these guys are going through, life is good. If he goes down, the standby will stop receiving hello messages and will take over within 10 seconds. This is the base config. We can tweak all kinds of stuff. But base config, standby router will take over within 10 seconds. Now let me compare how HSRP and, we'll throw VRRP in there, work compared to GLBP. So this is GLBP. When you set this up, one gateway will be assigned the Active Virtual Gateway role, AVG. Now the AVG is controlled by you. You set the priorities just like before, but it has, unlike the other protocols, it has nothing to do with actually forwarding traffic. It's more of like a management role, if you will. I'm saying this router is the manager router. All the other routers are going to act as active virtual forwarders, AVFs. Now, truth be told, this router, even though it's the AVG, will also be an active virtual forwarder. These are the workhorses. These are the routers that are forwarding traffic. So here's how it all works. You might say, well, what advantage does he have by being the AVG? Not really an advantage, just the manager. The AVG is the one responsible for responding to ARP requests. So let's just say same scenario as before, 10.1.1.0/24. We've got this guy, let's just say, is the .2. This guy is the .3. It's the same thing as HSRP. GLBP doesn't allow you to assign the virtual as one of the IP addresses, but we come up with a virtual as .1, right? So this is the phantom IP address. So the AVG is the one responsible for responding to ARP requests for that IP address. But with GLBP, there's one distinct difference. It will generate a unique MAC address for every active virtual forwarder in the cluster. Okay, so let's play out the scenario. Here's the pieces in place. Let's say this is PC number 1, right? He comes and says, hey, I want to get to the internet. ARP, what is the MAC address of dyslexia? What is the MAC address of my gateway? The AVG gets that ARP request and responds and says, oh, actually, it's going to be 1111111. That's the last 4 of that MAC address, right? And he goes, oh, okay, great. Thanks. I'm going to start going through you because he is the one that responds to that MAC address 1111. This guy responds to 2222, which is this MAC address right here. So PC number 2, who just appeared on the network, sends out an ARP request and says, hi, I'd like to get to my default gateway. Hello, who is 10.1.1.1? The active virtual gateway replies and says, oh, yeah, that's me. I'm 1111112222. So he hands out, the active virtual gateway hands out the MAC address of the secondary router. The third ARP request to come in will get the MAC address of the first router. Fourth will get the MAC address of the second router. So the way it works, isn't that creative? You know, somebody at Gateway was like, I'm the man, I thought of that. Somebody came out there and said, okay, we can get some load balancing here by handing out different virtual MAC addresses, and it's not limited to 2. You can keep adding routers to this cluster, this group of GLBP routers, and it can start handing out MAC addresses for each one of them. Matter of fact, you can even control how often each MAC address gets handed out. I can say, well, I want MAC address 1 handed out maybe 40% of the time because he has a better internet connection. MAC address 2 gets 20% of the time. MAC address 3 gets 30% of the time. You see what I mean? You can actually come up with different algorithms of how often each of these get handed out based on how much bandwidth they have for their internet connection. Now, the AVG role can be transferred. So this management role, if this one goes down, it's not like the whole cluster of routers go with it. It's once again a priority system to where this guy will take over as the AVG, as the manager based on his priority, and just start doling out the MAC addresses. And he will also take over for the first one's MAC address. So he'll respond to both MAC addresses. I know I added a couple more routers, but now let's just go back to 2. He'll respond for both of those phantom MAC addresses, so we still have a level of redundancy. Just like HSRP, tweakable, tunable, hello messages are sent once every 3 seconds. They are considered dead after 10 seconds, but you can tune that to whatever you'd like. So there are the concepts. The configuration will be in the next nugget. HSRP, VRRP, GLBP, all very good, very redundant protocols that give us a level of redundancy at layer 3. I hope this has been informative for you, and I'd like to thank you for viewing.